for this university, the team mascot is the Pomona. What's the Pomona?
Yeah, the angle of the
Mustang. First year at Nationals. Taylor Henry. And Taylor.
It's right there. We're going to take it home to the movies. I'll have to ask this question. All right. Yeah. Yeah, I'll try and download that stuff now. You take a look at it. So I got to pull the record too. Paper trail.
Madison, Wisconsin. There's a soccer, food, and backpack.
Basically, I'm going to speak about a bridge we have back home in Ecuador. This is a bridge site. Here's Ecuador in the northern part of South America. The bridge was located on the western end of Manabi province, linking two cities, Bahia, Caracas, and San Vicente. Two cities always linked by ferries and small vessels. It's a estuary zone with tidal water influence. So this is a basic data for a bridge. It's almost 2 kilometers long. The typical pier span was 45 meters. We had a deck formed by precast concrete beams and a cast-in-place concrete slab. The project was treated as a fast-track project. The government gave the contract before the designs were finished. So we were already building the access ramps before we were even drilling piles, dragging piles, sorry, in the middle of the story. These are the geotechnical conditions. This is a very simplified graph of what we found because in most rivers the soil was highly variable. But the main strata we found were on the top, these sands from 20 to 30 meters high. This is a seismic zone, so there were liquefiable sands, polyrated. The second layer we found was viable clay. We had thickness ranging from 25 to 30 meters, and was also loose to very loose in some parts, and then in some other parts was very stiff clay. So really very viable. We almost had to account for every tier. And then on the bottom we had some weather rock of almost 70 to 80 meters deep. In some, I highlighted this chart over here. In some parts we found non-liquefiable sand between the loose sand and the clay, but it was almost negligible. Only in 2 piers it was really taken into account for the design. Well, this is a basic schematic of a typical pier. We used steel valve pipes, 121 meters in diameter. They were formed by 20 millimeters thin A58 8 steel plates. In some points, we used all 9 piles to account for settlements. In some points, the center pile, number 5, was not driven, and this means we were reinforced to take into account the additional stresses. The piles were designed to screen friction because the rock was really deep, so we decided to just work by skin friction on the clay. Well, as I mentioned before, the design had to take into account the liquefaction at the site. So to confirm our designs, we use pile testing by high-strength dynamic methods with a CAD analysis. We had a lot of testing, really a lot more than you will have in a standard project, because we were not only taking into account quality assurance, but we were also trying to get research data. So it was a lot of testing, more than you will need. These are typical results for testing. These are the design values against measure values in some peers, just a small sample. Over 40 peers we installed, and we tested each and every one of the peers, at least 2 or 3 piles per peer. As you can see, during the design, we had more friction than tip, but it was still relatively balanced. During the testing phase, we found out that the tip really didn't perform as we expected. You can see really low values compared to the design values on the tip. But the friction was larger than we expected. So that compensated a little bit things. Also, the design loads we needed were around 3,000 to 5,000 kilonewtons. As you can see, we usually were a little bit higher than that. Most of the time it was due to settlement. We had to drive a little deeper just to make sure that the piles will settle. And this is a capacity profile. This is from a work that my brother did, so I just had a little help from him with this. We found out that this is a catwalk, and these are all the design methods. So we found out that most of the design methods were over the real values we had measured. Only the beta method was lower than that, was the only conservative one. So usually you should try to take into account a little bit higher, at least for our soils, we found out that we should take into account a little bit higher safety factors if we want to use this formula. Then also by the shape of the curves we obtained, we found that the Meyerhoff method is the one that best suits the kind of soils we had in the project. So probably in the next design for the next projects, we'll probably be applying the Meyerhoff method. That's for sands. For clays, we found out that pretty much we can use any method with just the appropriate safety factors. Then, this is just for showing purposes. This is a catwalk curve for this pier. This is pier 26. And you can see that the tip is very low, and this is all skin friction. So basically, the pile is working skin friction right now. We also had some research pertaining to something that Eric was talking about before. We didn't have enough time to do any really long-term capacity. Actually, this will be medium-term. But we tested piles up to 70 days just to see the increase in capacity compared to the first day we installed them. These are only for Pier 44 and 46. Sadly, because of the construction process and the logistics to take the testing equipment to the site, the testing equipment will come every 3 or 4 months. And so we couldn't take more tests like this in other piles because the construction schedule will allow us. But at least we got it on these piers. So we had this is a composite of all the piles tested in those piers. So we found out that approximately 1 to 2 days after installing, we had 3 times the capacity we had when we just tested the pile after the driving. In 3 days, it will be almost 4 times as much. And this is almost a little bit over 2 months. We get a little more than 4 times the original capacity. So that also helped